are very happy to invite Dr. Subramanian to come to give us a talk. Dr. Sathya completed his PhD in quantum computing at the University of Cambridge under the supervision of Professor Richard Doza, and is currently a research fellow in the Department of Computer Science at the University of Warwick. And the Foundations of Classical and Quantum Verifiable Computing Project, which is led by Dr. Tam Gill. His primary interests are quantum algorithm and computation complexity theory. So let's welcome him.
So thanks, Ming-Chen, for the introduction. So first, I'd like to thank Ming-Chen and Min-Shu for inviting me to speak in this seminar. And good morning to everyone. What I'll be talking about today is some recent work that we have about sublinear algorithms, sublinear quantum query algorithms for estimating the von Neumann entropy of an unknown quantum density matrix. So this is
your PowerPoint is missing.
Sorry, Ming-Chen.
We cannot see your slide.
Oh, sorry. Let me share it again. Can you see it now?
Yes.
Okay. Please let me know if it stops sharing in the middle, or if there's any problem with the audio. Please let me know in the middle. So I'm going to be talking about sublinear quantum algorithms for estimating von Neumann entropy, and this is joint work with Tom Gore, who's my postdoc supervisor at the University of Warwick, and our own Min-Shu. I'd like to keep the talk very informal and more of a discussion. So please feel free to interrupt and ask questions during the middle if anything is unclear, or if you'd like to ask for more details on any point that I'm talking about. The way I've structured the talk today is I'd like to first introduce some background and motivate why we want to estimate the entropy, and in particular, what kind of estimate do we want? Because there are two popular kinds of estimations for unknown quantities. One is additive and one is multiplicative. And then I would introduce what kind of input model we work with, in what form does our quantum algorithm access the unknown input. And then there's a lot of related work on this topic. Our work on multiplicative estimation of von Neumann entropy comes in a long line of about 20 years of work. It's you could perhaps think of it as the latest in a series of 2 decades of work. And then I'll go into the technical details a little bit. I won't go into all the details of the proof, but I will introduce what the estimator is that we use, because the problem is essentially one of statistics. So we have an unknown distribution, and we're trying to estimate a quantity, a function which depends on the probability masses of this distribution. So I'll introduce what estimator we use, and then I will give an overview of the algorithm that achieves what we want. That is, output an estimate of the von Neumann entropy using a sublinear number of queries to the quantum state. And I will also quickly go over the techniques. I'd like to gently introduce the main techniques. The main machinery consists of quantum singular value transformations, which was a beautiful framework for designing quantum algorithms that was introduced by Andras Gillian and others in 2019. Okay, so with that, I'll start with the main part of the talk. So to get definitions out of the way first, suppose we have a probability distribution, a discrete distribution over some set of labels, 1 up to n. We can define its Shannon entropy in the usual way. So this is h of p is minus summation over pi times log of pi. And we can think of the log as being taken to base 2 for all our purposes. And this I'm sure everyone is familiar with, so I will not spend too much time on this. And we have the analogous quantity called the von Neumann entropy of a quantum state, in particular a quantum mixed state. And we know that a mixed state, the most general description of a mixed quantum state is in terms of a positive semi-definite matrix known as its density matrix. And it's normalized to have trace 1. So rho is an n by n matrix, which is positive semi-definite and has trace 1. And then the Shannon entropy of this state is defined by negative of the trace of rho times log rho, where log rho is the operator function log. And equivalently, we can think of this as the Shannon entropy of the spectrum of eigenvalues of rho. So because rho has trace 1, the eigenvalues of rho form a probability distribution, that is, they sum to 1. And S of rho is essentially H of P, where P is defined by the spectrum of rho. So these quantities, the Shannon and the von Neumann entropy, are ubiquitous in information theory. And I think most of you are, in fact, information theorists, and you're familiar with how important these quantities are for tasks ranging from compression in coding and cryptography to condensed matter theory when you're studying the entropy of some Ising models or other kinds of condensed matter states. And then they can be used in the study of phase transitions, in thermodynamics, and a variety of other applications. They also find a lot of applications in theoretical computer science when you're studying algorithms for tasks such as pattern matching or even compression and neural networks. Okay, so with those definitions out of the way, our work is on estimating entropy. So what notion of estimation are we thinking of? So the most popular thing that one would think about if you say you want to approximate an unknown quantity is estimating it to additive precision. So if the unknown quantity is x and its estimate that we are going to get is x tilde, then an additive precision estimate satisfies that the estimate lies between x minus epsilon and x plus epsilon, or like equivalently, the absolute value of x minus x tilde is less than epsilon. So this is the standard definition of additive precision. Now, in this work, we'll be interested in multiplicative precision estimates, or rather estimates to within a multiplicative factor. So given a factor gamma larger than 1, a multiplicative estimate of the quantity x must satisfy this inequality here, that is, x scaled down by gamma, x divided by gamma, should be less than our estimate x tilde, which in turn should be less than x scaled up by gamma. So for example, if you choose gamma to be 2, this means that you should output a quantity x tilde, which lies between half the true value and 2 times the true value. It's an interesting notion of estimation, which finds a lot of use in theoretical computer science, especially including in the study of complexity classes like NP, where for many problems, we don't know how to solve the problem exactly. And we may also not know how to solve the problem efficiently up to additive precision, but we might have efficient algorithms to solve the problem to within multiplicative precision. So for example, if you think of something like the traveling salesman problem or other kinds of decision versions of optimization problems, we may not be able to approach the optimal solution to within plus or minus epsilon precision, but we may be able to approximate the optimal solution to within a factor. So we may have a solution which is between half and 2 times the optimal solution. And so estimation to within a multiplicative factor is an important tool, and it's well studied in classical complexity theory. So why is multiplicative estimation so good? Why is it used in all these situations? So on the one hand, it's very general. It's general in the sense that if you have an unknown quantity which is bounded, for example, the entropy is bounded above. So if you have the entropy of an n-dimensional distribution, we know that it's bounded above by log n. For such quantities, we can always recover an additive estimate by using a multiplicative estimate. and the overhead in complexity is small. In fact, it will be sub-polynomial. So the notation here, I think you may be probably familiar with it, but I'll just go over it anyway. Little O of 1 is a quantity which decays faster than a constant. So for example, 1 divided by log n is a quantity which is little O of 1 because it decays as n goes to infinity. So just to quickly see why choosing a multiplicative, sorry, is there a question? Okay, go on. So the reason why choosing gamma to be 1 plus epsilon over log n recovers additive precision is, as you can see here, so the definition of multiplicative precision, if we go back to the previous slide. So I just want to make sure that these notions become familiar as we go further into the talk. So on the left-hand side, we have x over gamma is less than x delta. And in this case, gamma is 1 plus epsilon over log n. So on the third point here, can you see my cursor, Ming Chen?
You hear me?
Yes, can you hear me?
Yes, but your cursor seems not.
I see, it's not visible. Okay, no worries.
Yeah, it's moving, yeah.
Okay. Oh, okay. So the quantity that I'm circling here, which is the third component in this inequality, this is h divided by gamma because gamma is 1 plus epsilon over log n. And what we have is that by using the binomial theorem, we can see that 1 divided by 1 plus epsilon over log n is larger than 1 minus epsilon over log n. And because h is smaller than log n, this quantity in turn is larger than h minus epsilon. And on the right-hand side, we see that gamma times h. So this is, again, in the definition of multiplicative precision. On the right-hand side, we have gamma times x. And here we have 1 plus epsilon over log n times h. And again, because h is bounded by log n, we see that this is less than h plus epsilon. So this is why choosing, obtaining a multiplicative precision estimate also recovers additive estimates if we choose the multiplicative factor appropriately. So that's one reason why we're interested in multiplicative estimates. Another reason.
And can you explain the complexity overhead? It means it's about linear time complexity.
It's sublinear. So the little o of 1 here represents a quantity which is less than a constant. Okay, so for example, it may be 1 over log n.
Okay, I see.
Yeah, and since we are interested in the asymptotic complexity, when n goes to infinity, this factor will go to 1.
Okay.
Yeah.
Okay, thank you.
Is that clear?
Yes.
Okay. So this is one reason that multiplicative estimates are useful and they're general. Another reason is if you have a problem such as deciding whether the entropy of an unknown distribution is high or low. So in what sense do we mean high or low? So if you're given some thresholds, h2 and h1, such that h2 is less than h1 and they both lie between 0 and log n, and you want to know whether the unknown distribution has entropy larger than h1 or smaller than h2, then this problem can be solved by using a gamma approximation. It can, of course, also be solved with an additive approximation, but the problem is it's harder to choose the precision of additive estimation. For these tasks, it's harder to choose the precision of additive estimation because it would depend on the gap in a somewhat non-trivial way. And so here, what we can do is if we choose the multiplicative factor of approximation to be square root of h1 over h2, once again, we recall the guarantee that the multiplicative approximate gives us, which is that 1 divided by gamma times the true value is a lower bound for the estimate, and gamma times the true value is an upper bound for the estimate. So here, choosing gamma equals square root of h1 over h2, we see that in the case where the entropy is actually low, the estimate which the algorithm outputs is bounded by this quantity, which is square root of h1, h2. And in the case where the true entropy is high, it's lower bounded by the quantity h1 divided by gamma, which is actually, if you also see, this is also square root of h1, h2, which means by choosing gamma appropriately, depending on the threshold, we can decide whether the unknown distribution has high or low entropy. And more generally, this kind of problem comes under the study of what's called distributional property testing, where the goal is usually slightly different, So rather than deciding whether the entropy is high or low, we want to decide whether the entropy is high or the given distribution is far from every distribution which has high entropy. And far from every distribution can be defined in terms of the total variation distance usually. And for solving distributional property testing problems, it's found that usually we require multiplicative estimates of the unknown quantity rather than additive estimates. So this is some motivation for why multiplicative estimation is an important problem. And I hope conveyed at least a couple of reasons for this. So the generality in the sense that you can recover additive estimates and applications to testing problems. Okay, so now we know what we're going to do. And the next thing we need to know is how is the unknown distribution accessed? So in particular, we're going to consider quantum algorithms. So I'm assuming some familiarity with the kind of bracket notation and the notion that a quantum algorithm is basically represented by a unitary, which acts on some input state. And then finally, we measure the output state. So just assuming this is preliminary. And then, so the quantum algorithm has to be implemented by a unitary running on a quantum state. And this means the input, which in our case is an unknown classical distribution, or an unknown quantum state. So because we're interested in estimating both Shannon and von Neumann entropies. So in the Shannon case, we have an unknown classical distribution for which we want an estimate of the entropy. And in the quantum case, we have an unknown quantum mixed state. So the way the quantum algorithm accesses the input can be one of three popular models which have been defined and studied in the literature. And I'll go over all three. The first one is what's called the frequency vector model. So in this case, as you can see in the definition here, you have a vector v which represents some unknown distribution. And the way in which it represents the distribution, as you can see from the example here, if v is this vector of length 6, it encodes a distribution over the labels 1, 2, and 3, where the probabilities are given by half, 1/3, and 1/6 according to this condition. So pi, in this case, for example, p1 is the number of times 1 occurs divided by the length of the vector, which is 3 divided by 6, and that's what gives you half. And for the quantum algorithm, what we do is that we have a unitary which can access the vector v in superposition. So I here is an index which indexes the length of the vector, and 0 is an ancillary register in which you will load the value of the label in that index. So this model is, so we use this model, the frequency vector model, in our work, actually for proving lower bounds. And in this talk, I think I probably won't have time to go into the details of lower bounds, but I've included the definitions here anyway. So, and in any case, this is one of the fundamental input models used for quantum algorithms accessing classical distributions. So it's good to go over it. The other second most popular model is the so-called quantum samples model. So in this case, you have a unitary U, which prepares a state of this form in the middle. So the d-1 here should be actually an n-1 because I'm thinking of n-dimensional states. That is, states or distributions defined on n labels. So what is the property that this state has which we like? Basically, if we measure it in the computational basis, which is I here is the computational basis, we see that the probability of outcome I is the amplitude of outcome I squared, which is in this case pi. So this state exactly represents the unknown distribution in the sense that if we measure it, we can draw a sample according to the unknown distribution. So this model, the quantum samples model, has been studied a lot in the quantum machine learning setting, especially in the quantum statistical learning framework, where people have been able to prove both upper and lower bounds on the sample complexity of learning. And it was first studied, I think, in 1998 by Batu and Jackson in their famous paper on quantum machine learning. And it's known to be a very powerful model in the sense that many tasks can be solved trivially if you have this input model. Many tasks can be solved with extremely low complexity if we have this input model. So now I'll go on to the third input model, which is the most general one and the one which we use in this work. It's called the Purified quantum query access model. So it's straightforward to define. For an unknown density matrix rho, what we have is a unitary which prepares a purification of rho. So I think most of you may be familiar with the notion of purification, but all we need to know here is that it prepares a pure state such that if we ignore the second register, which is the ancillary register, that is, if we trace it out, so tracing out a register amounts to ignoring that it is actually present. So if we do this, then measuring the state corresponds to accessing the density matrix rho. So if you trace out the register here, which has phi I, then you can see that you recover a matrix which has eigenvalues pi, which are going to be the eigenvalues of the unknown density matrix rho. So what you're getting as input is a unitary which prepares a purification of the unknown density matrix. Now it may seem a little bit contrived or artificial at first, but it's actually a very natural input model because in quantum algorithms, usually we prepare some state which is joint over some system and some ancilla. And usually we have access to both the system and the ancilla. It may be the case that when we are thinking of decoherence and other things like noise, we are thinking of a system and an environment where we don't have access to the environment. But in quantum algorithms as such, where we do the computation, we're usually thinking of a system plus an ancilla, where both the system and ancilla are in our control, and we may only be interested in the system state. So this is captured in this model because you can think of the phi state here as being part of an ancillary system which we are not interested in, and the psi state as representing the system register. And therefore, this model is very general because most quantum algorithms will produce an output of this form. So if you have a task where you want to estimate the entropy of some state or distribution, which is coming as the output of some other quantum algorithm, then the purified quantum access model is pretty much the right model to be thinking. And then, of course, the psi and phi here are essentially orthonormal bases for the system and ancillary subspaces. So this is just a point to keep in mind. And there's a small simplification when we are thinking of classical distributions. So I mentioned that 2 captures unknown density matrices rho. Classical probability distributions can be thought of as density matrices which are diagonal in the computational basis. So the eigenvalues of the density matrix should correspond to the probabilities P1 up to Pn. And in particular, these eigenvalues correspond to the eigenvectors, which are just the computational basis states here. Apologies. So the simplification is, if you can see my cursor, in 3 compared to 2, we don't have unknown states phi I in the second register, but the second register is a known state, which is the computational basis states. This is the simplification that we get when we consider classical probability distributions in the purified access input model. Basically, the idea is that it's easy to purify a diagonal density matrix, which is diagonal in the computational basis. Okay, so 2 and 3 are kind of the main characters for the rest of this talk. They'll be the main players which we use. So, and I can come back here to remind you what they are. And okay, so are there any questions so far?
Yeah.
Okay. Yeah. So I'll move on then. So before we actually go into into what we do, let me try and present to you like the background of work on this topic, on the topic of entropy estimation, and kind of show you where our work fits in. So as I mentioned before, estimation could be the task of outputting an additive estimate or a multiplicative estimate. And we could think of classical algorithms for this task or quantum algorithms for this task. And in particular, this table is talking about Shannon entropy. So it's either classical or quantum algorithms for classical distributions. And in the additive case, we have these 2 seminal works of Wu and Yang and Jiao et al., who showed that essentially with n over epsilon log n samples, and the capital theta here represents that this is both an upper bound on the sample complexity as well as a lower bound. So this number of samples suffices, and it's also necessary. for estimating the Shannon entropy to precision epsilon. So this work is very much kind of statistical in nature. They define a particular kind of estimator, and they study the properties of this estimator with respect to a hypothesis testing setting. So they consider the minimax error of the estimator, and they consider its convergence to the true value. So the same task can also be studied in the quantum framework. That is, we have quantum algorithms accessing a classical distribution, and we want to know what is the complexity, the sample complexity or the query complexity of estimating the entropy. So I think, I've not mentioned this before, so now is a good time to clarify. So the classical sample complexity is something very easy to understand. So we have an unknown distribution, and we are just drawing more and more samples from it. And the number of samples which we draw is the sample complexity. The quantum analog of the sample complexity in the input models which I have described so far is the query complexity, because what do we have in the quantum setting? What we have is these oracles, right? And these oracles are used on some state of our choice during the algorithm. So the query complexity is the number of times we use this oracle. And in a sense, it corresponds to the sample complexity, because as we saw, for example, with quantum samples, as we saw, if we use the oracle once and we measure the state, then we draw a sample. So that subroutine of applying the oracle and measuring the state is analogous to the classical action of drawing a sample. And therefore, we can think of the number of times we use the oracle as the information theoretic measure of the resource complexity. So it's a query complexity, because we may not actually measure the state after each time we apply the oracle. We may not actually measure the state. However, if we measure the state, we can think of a thought experiment where we measure the state, and then this actually corresponds to a sample. So the number of times we apply the oracle, it's called the query complexity, and it's the analog of the sample complexity. So in this setting, Gillian and Lee and Wu showed that you can achieve this upper bound of essentially square root of the dimension for estimating Shannon entropy to additive precision. And just a minor point here, Lee and Wu used the frequency vector input model, whereas Gillian and Lee used the purified query access input model. And the first thing you would notice is that in the classical case, the complexity is linear in the dimension n, whereas in the quantum case, it's square root of n. So there's a quadratic improvement. And then subsequently, Boone, Kothari, and Taylor also showed that there's a lower bound of square root of n for this task in the quantum setting. So essentially, square root of n for this task is a tight bound. Then going to the multiplicative estimation setting, in the classical setting, this was first studied by Batu et al. In 2002. But subsequently, it was improved, and the best known result is from Valiant and Valiant in 2011, where they showed that if you want to obtain an estimate to within multiplicative factor gamma larger than 1, then it suffices to use n to the power 1 over gamma squared plus some small decaying constant, or a small decaying exponent, number of samples. And this is nice, because if you choose, as we saw earlier, for example, if you choose gamma equals 2, then you can see that this becomes n to the power 1 over 4. So in comparison to additive estimates, where we require a linear number of samples, for multiplicative estimates, it may be the case that we only need a sublinear number of samples. In fact, significantly lower. The n to the power 1 over 4 can be significantly lower than n in the asymptotic limit when you're thinking of very large alphabets. And then subsequently, Valiant also showed that there's a matching lower bound for this task. So the little o of 1 here is, you can pretty much ignore it for our purposes. It's a technical point which is basically representing a small overhead that comes from logarithmic factors. So the upper bound and the lower bound are essentially matching. If you take n to infinity, then the little o of 1 factors become 0, and the bounds essentially match. So in this work, we were motivated first by the question of this quadratic improvement, which you can see in the estimate in the epsilon additive case. So you can see that classically there's linear complexity n, and quantumly there's complexity square root of n. So our first question was, if we wanted to obtain gamma multiplicative estimates of Shannon entropy with a quantum algorithm, can we get a similar quadratic speedup? And indeed, we show that this is possible. So if you compare the last box in this table, which is our work, we show that you can improve the classical sample complexity of valiant invariant from n to the 1 over gamma squared to n to the 1 over 2 gamma squared. That is basically square root of n to the 1 over gamma squared. So we get a quadratic improvement in the information theoretic complexity for gamma multiplicative estimation of Shannon entropy. However, for the lower bound side, we were unable to prove a tight lower bound. So far, what we have is a lower bound, which is n to the power 1 over 3 gamma squared. So you can see that there's a gap between 1 over 2 gamma squared and 1 over 3 gamma squared. And our technique for the lower bound essentially is a straightforward reduction from the collision problem. So for those of you who are familiar with this, it may ring a bell. For others, I'll try and go into the details later. Okay, so that was one of the motivations for our work, estimating Shannon entropy with a quadratic improvement. The other thing is von Neumann entropy. So that's the actual title of this talk, and I'll try to emphasize why this is important. So if you look at estimates of von Neumann entropy to additive precision, this was studied, for example, by Acharya et al. In quite a recent work. And they work in a model where what you have is copies of the unknown density matrix row. So what you have is, say, for example, you have an apparatus or something in the lab, a system which can be prepared in the state row. So you have independent copies of row. And what you're allowed to do is measure these copies. You're allowed to apply some unitary to these copies, and you're allowed to measure them. So Acharya et al. Showed that in this model for epsilon additive estimation of von Neumann entropy, you essentially require n squared copies. So n is the dimension of the state, if you remember. And this means you need essentially quadratic in the dimension number of copies of the state. They also showed essentially a matching lower bound. So as a function of n, the lower bound is also n squared, so they match. As a technical point, the lower bound is not matching as a function of epsilon. So there's still a gap there, which is an open problem to close. And then coming to other input models for quantum states, we saw that the most general input model is the purified quantum queries model. And in this input model for epsilon additive estimates of the von Neumann entropy, Gillian and Lee in 2019 showed that you can do it with a linear number of queries. So again, you can see that there's essentially a quadratic improvement compared to the copies input model and the purified access input model. The copies input model can be thought of as a somewhat classical input model, in the sense that, so classically, for classical probability distributions, what we do is we draw samples from the unknown distribution, right? And having quantum states and simply measuring them is analogous to drawing samples from the classical distribution. So the only thing that has changed is that the object which we are sampling from is now a quantum object. It's a quantum density matrix. But with copies, all you can do is sample from them. Whereas the intuition is that with purified quantum queries, you have a little bit more information. You actually have a unitary which is preparing this unknown state, and you actually have access to the ancillary system with which the state is entangled. And intuitively, you can use this additional information to reduce the complexity. And that's essentially what's happening here. And then in our work, we're looking at the problem of gamma multiplicative estimation. And going by what we saw on the previous slide, which is that for gamma multiplicative estimation of Shannon entropies, it is possible to get sublinear complexity. We were motivated to ask whether you can get sublinear complexity for estimating von Neumann entropy also. And we answered this question positively. So we show that in the purified quantum query access model, with n to the power half plus 1 over 2 gamma squared queries, we can estimate von Neumann entropy to within a multiplicative factor gamma. And again, I'd like to remind you that gamma is larger than 1. So the exponent here is actually less than 1. So for example, if you take gamma to be 2, it becomes half plus 1/8, which is less than 3/4. And the same lower bound, so I won't remark much about the lower bound here. It's essentially the same lower bound that we have for the Shannon entropy case, and it remains an open problem to tighten this. So the reason why this is very significant, the reason why a sublinear algorithm for estimating for Neumann entropy is very significant is that, to the best of our knowledge, all preceding works that estimate any property of the spectrum of a quantum state require complexity that is at least linear in the dimension of the state. So for example, the most naive method that you can use for doing this is you can perform full tomography of the state, and then you can, this gives you access to the entire spectrum, and then you can compute whatever function you want. This is the most naive way of doing it, but we know that tomography has complexity that scales quadratically in the dimension of the state. And when we're thinking of large, high-dimensional states, this can be prohibitively costly. And what we're showing is essentially that with sublinear queries to the state, there exist global properties which you can still measure in a useful way. And in particular, the global property that we demonstrate this for is the for Neumann entropy, which, as we all know, is a very useful property of quantum states. Okay, so with that, I can.
There is a question.
Oh, sorry.
Hi, can you hear me?
Yes, I can hear you.
Yeah. Is it one of these?
Yes, let's speak that.
Okay. Yeah, I was just wondering about the gamma. So at this point, gamma is arbitrary, right? It just
yes. Yeah, okay. It's arbitrary and it's larger than 1.
And I guess, so there is optimality for some cases, or so for like at this point, the bound holds for all gamma greater or equal than 1?
Yes, but, yes. It cannot be equal to 1, but it's for gamma greater than 1. It can be arbitrarily close to 1.
And then, but yeah, I'm just thinking, like, I guess there is optimality for some, like of choosing this gamma, or?
So by optimality, do you mean matching lower bound, or?
Yeah, I guess like saturating the bound or something like that for the particular.
I see, right. Okay, no, so actually the bound is, it's a function of gamma. So for a given value of gamma, the upper bound is, this function of gamma, and the lower bound is this corresponding function of gamma. I'm sorry, is that what you're asking? I'm not sure if I understand the question.
I'm just thinking, so there is an upper and lower bound on this, on the von Neumann entropy, and then, so I'm just thinking if this gamma, there is an optimal way that you can choose it so that the bounds, for example, are saturated.
Oh,
so
I see. Okay. Okay, so maybe I think what I should clarify is that the gamma is an input parameter. So you can specify to me how good an approximation that you want. So it's similar to epsilon in the additive case, right? So depending on the application which you have, you may require some value of epsilon. Similarly, depending on the application which you have, you may require some value of gamma. So what the algorithm does is that it asks you for what you want. Like, do you want gamma to be some value? And for this value of gamma, using a number of queries which scales as the upper bound of the complexity, it gives you an answer. It gives you an estimate for that value of gamma. So gamma is actually an input parameter.
So I guess, for example, with epsilon, I would think of epsilon taking an epsilon very small would be like the best. So I guess with gamma would be to take a gamma very close to 1, maybe?
Exactly, okay. Yeah. Okay. But it depends on the application. So in some applications, you may not need gamma which is too close to 1. You may need only a gamma which is, for example, for some applications, 1.1 may suffice. And for some applications, you may need 1.001. And for some applications, maybe even 2 suffices.
Okay. All right, thanks.
Okay. So are there any other questions?
I think it's good.
Okay, so go ahead. Okay, so Minchen, how much time do I have?
About 20 minutes.
Okay. So I'll just quickly go over our strategy for solving this problem for the upper bounds. I think there won't be too much time to go into the lower bounds. So the first thing is what is the estimator that achieves these complexities? So how do we actually estimate the entropy? The intuition is that we divide the domain into two sets. So one set consists of so-called big or heavy elements, and this is the set B of all the labels. So we don't actually know the labels, but we can theoretically divide them. It's all the labels which have probability mass larger than some threshold beta. And S is the set of small or lightweight elements which have probability mass less than beta. So the intuition behind this is that when we draw samples from a distribution, the points which we see, the labels which we see most often are the ones which have high mass, high probability. And the labels which have low probability don't appear so often. So and in particular, if a particular label has probability P, then we expect that we have to draw at least 1 over P samples in order to see at least one sample which is equal to X, this unknown sample that we started with. So the main bottleneck or the main barrier in estimating the entropy is estimating the low weight elements, because if you want to see a low weight element, you need to draw a lot of samples. But we don't want to draw a lot of samples. We want to minimize the number of samples that we draw. And to make a trade-off between how many samples we draw and the quality of the approximation, we choose a threshold beta. So, and as you all know from just basic statistics and Chernoff bounds, as we draw more and more samples, we get better and better estimates of the probabilities themselves and of various functions of the probabilities. So what we want is a trade-off between how many samples we draw and the quality of the approximation. And to achieve this, to control this trade-off, we introduce a threshold beta, which divides the heavy and light weights. And what we want to do is make this threshold as large as possible, because we are going to, in some sense, we are going to ignore the elements which are smaller than the threshold. So we're going to ignore the elements which have very low probability in a high level. So this is not exactly true, but at a high level, that's what we want to do. And later on, what we actually do is we choose beta to scale as a function of the input parameter, which is gamma. So gamma controls the quality of the approximation. And we will choose a threshold that depends on gamma. In particular, it depends in this form. So beta is equal to n to the power 1 over gamma squared. And then the key point that we use is that the Shannon entropy is linear when you consider subsets of the labels. So the notation here refers to basically the original definition of the Shannon entropy, which is summation pi log pi, but now I is restricted to b. So we just sum up the entropies for all the labels which have high mass when we consider HP of P. And correspondingly for HP of S, we just sum up the entropies, the pi log pi for all the elements which have low weight. So that's our strategy. So the strategy, this is also the classical strategy. This is what is used in the classical algorithm, which achieves the n to the power 1 over gamma squared upper bound, which is to estimate the entropy, the contribution of the heavy elements to the entropy and the contribution of the light elements to the entropy separately. Okay. And so I said that we will essentially ignore the contribution of the lightweight elements to the entropy. To make it more clear what I mean by this, what we can say is that if the lightweight elements have a total weight, so WP of S here represents the total weight, that is the summation of the probabilities for all the labels which lie inside S. So if the total weight of the lightweight elements is some quantity W, then we can bound the contribution of the lightweight elements to the entropy, which is this HP of S here. We can bound this quantity both from above and below as a function of the total weight of those elements. And this is easy to prove. So the upper bound is achieved when the total weight is distributed uniformly over all the points, and the lower bound is achieved similarly when you make as many elements have high mass as possible. So because if we recall, the threshold is beta for lightweight elements. So this is similar to the optimization of the entropy itself. So the way that you achieve the highest and lowest entropies for a distribution. So this lemma, so this inequality gives us the intuition that when we choose beta equals n to the power 1 over gamma squared, so just plugging in beta equals n to the power 1 over gamma squared here, we can recover this inequality. And what we notice from here is that this quantity on the left here, the weight times log n divided by gamma, is bounded above by gamma times the contribution of the lightweight elements to the entropy. And this gives us, and what you recall is also that in the definition of multiplicative approximation, suppose we consider only the lightweight elements, forget the heavyweight elements now, and just consider the lightweight elements. The quantity that appears in the middle here is what should appear on the right-hand side of the multiplicative estimate. So it's gamma, the estimate should be bounded above by gamma times the true value of the entropy. And so we see that this quantity satisfies this condition, and therefore the quantity on the left-hand side in the middle here, which I'm now circling, is going to be the quantity of interest, which we are going to use as an estimate of the entropy of the lightweight elements. And so what we will actually do is we will choose the estimator for the unknown entropy to be a multiplicative estimate for the heavy elements plus a multiplicative estimate for the light elements. And in particular, the multiplicative estimate for the light elements does not need to individually measure the probabilities of the lightweight elements. It only needs to measure the total mass of the lightweight elements. And this is one of the key intuitions behind the speed up, both in the classical and the quantum case. The reason why multiplicative estimation requires sublinear complexity is that we can bundle up all the lightweight elements into one point. So if we have many elements which have exponentially small probability, we don't care about all of them. We don't care about the individual labels. We only need to consider all of them together as a single point, which has the total weight of WP of S. Okay, so that was just a bit of intuition behind how we handle lightweight elements. And I'll just quickly say what our main results are exactly. So, in the quantum purified query access model, we show that for estimating Shannon entropies, we obtain a quadratic improvement in the sample complexity. And essentially, the complexity is n to the power 1 over 2 gamma squared for our algorithm. And for estimating the von Neumann entropy of an unknown density matrix in the purified access model, we have a complexity that is n to the power half plus 1 over 2 gamma squared. So, and in particular, again, this is sublinear. So towards proving both of these theorems, the main algorithm or the technical tools that we use are quite recent on the one hand. So we have quantum singular value estimation and transformation. So I'll come to this quickly. And so again, this is just to recount what our algorithm does. So the first step is somewhat technical. So the user gives us some input value for the precision that he or she wants, gamma, and we will first scale it down by some factor. It's a technical point. And then depending on this quality of approximation, we choose the threshold, which I described on the previous slides. And with this threshold, we also choose a particular number of bits of precision. So I'll come to what this means. And then with this setting of parameters, we obtain an estimate of the entropy of the heavy elements, and we obtain an estimate of the weight of the light element. Once we do both of these estimation tasks, we combine them, as I showed on the previous slide, to form this estimator. And it can be shown, so it can be proved that this estimator actually satisfies the multiplicative precision condition that we saw on the first few slides. So yeah, just quickly, the main subroutines are estimating the entropy of the heavy elements and estimating the weight of the light elements, the total weight of the light elements. So yes, so the techniques that we use are essentially drawn from the quantum singular value transformation literature. So this is a technique that was first introduced to study the problem of Hamiltonian simulation in around 2009 or 10. And the main idea is that in quantum computing, we always implement unitaries, but sometimes we're interested in implementing non-unitary operations. So for example, if you have a system of linear equations like AX equals B, then to solve it, you want to invert the matrix A. And usually A may not be a unitary matrix. So this inversion operation corresponds to implementing something that is not unitary. So this technique was developed to address such problems. And the key idea is that we enlarge the space. So the first thing we do is that A is a matrix that acts on some system of dimension, let's say n. What we do is attach an ancilla and enlarge the space. Once we have enlarged the space, we have enough freedom. So the dots here in the equation here, we have enough degrees of freedom to convert it into a unitary. So we can consider a larger unitary. So we consider a larger space and a larger unitary such that one of its blocks is the target operation that we want. And this intuition can be generalized further. And so this target here, the first block here corresponds to projecting on 0, 0, right? Like if we think of the block structure of this matrix in the computational basis, then the top left corresponds to 0, 0. The next one corresponds to 0, 1. The next one corresponds to 1, 0. And the last one is 1, 1. So here we are essentially saying that there's a block which is encoded in the 0, 0 subspace. We can generalize this intuition further and say that it's embedded in some subspace which is distinguished by a projector pi and pi tilde. So I know this is a bit high level, but the idea is that once we have such an encoding, we can proceed to do a lot of other things with them. And the key intuition which allows us to obtain our speedup is that the purified access oracle, so I'm just recalling what the oracle was here. So we have U rho, which prepares a purification of the unknown density matrix rho. The purified access oracle can be converted into a projected unitary encoding of this operator. So pi, which has this form, square root of pi, pi I, 0, 0, I. In particular, what you will notice is that the summation here on the right-hand side represents a singular value decomposition. So like these are the right singular vectors, and these are the left singular vectors of the matrix P. And the singular values are square root of pi. So this is the second kind of key intuition which allows us to obtain our speedup. So the quantum algorithm is actually able to access square root of each of the probability masses. And the reason why this is good is that as we saw earlier, it's the lightweight elements which cause some problems. So when there are elements which occur with very low probability, estimating their probability is very hard because we need to draw many samples. But if we have access to the square root of the probability, because pi lies between 0 and 1, square root of pi is larger than pi. So for example, if you have a probability which is 1 over 4, square root of 1 over 4 is half, which is easier to deal with. So in some sense, the quantum algorithm is able to, like in an operational way, it's able to amplify the unknown probabilities. And in particular, it's able to amplify them by a quadratic factor, or rather, in a quadratic way. It can access the square roots of the probabilities. So what we do is we construct a block encoding. We take the purified access oracle, and we construct a block encoding of this matrix P, which has these as its singular values. And then, as we saw earlier, the strategy is to estimate the entropy of the heavy elements and the weight of the light elements separately. So we do exactly this. And then the tools that we use for this are quantum singular value transformations, quantum singular value estimation, and amplitude estimation, and then finally polynomial approximations of log. So I think I'm probably running out of time, so I won't go into some of the details here. And so amplitude estimation is a standard subroutine that many of you would have seen. The idea is that if you have a unitary which has this action, the unitary produces a state which has, in particular, an unknown amplitude p on one of its subspaces, which is flagged by 0. Amplitude estimation is an algorithm which allows you to estimate p. In particular, you can estimate p with additive precision epsilon using 1 over epsilon queries. And quantum singular value estimation is a kind of generalization of amplitude estimation. So instead of estimating the singular values, or instead of estimating the eigenvalues of a unitary, this allows you to estimate the singular values of an arbitrary matrix. And in particular, you can implement a map of the form 4. So you start with a state of this kind, and you can produce a state as on the right side, where what we have is an estimate qi of each of the singular values pi of some unknown matrix, which is performing this transformation. So these are just some of the algorithmic tools which go into a proof. So for the lightweight elements, so maybe I can just spend a minute on saying how this works. We start with the state that's prepared by the purified access oracle. And then the next step is to flag the lightweight elements. So what we want to estimate is the total weight of lightweight elements. And the way we do this is we need to be able to somehow coherently, in superposition, we need to be able to recognize the lightweight elements and the heavyweight elements separately. So to do this, we perform quantum singular value estimation. And as you can see here, the last register now contains an estimate of each of the QIs. And we choose the precision for singular value estimation in a clever way, such that this QI is always 0 whenever PI is a lightweight element. And in particular, that produces a state as on the third line here. And if you compare this to the amplitude, the quantum amplitude estimation framework, this is exactly matching the state on the right-hand side of quantum amplitude estimation. So we have a state where the total amplitude of the state, which is marked by 0, contains the sum of the probabilities of the lightweight elements, which is exactly WP of S. And once we do this, we simply estimate the amplitude of the first part of the state using quantum amplitude estimation. Once again, we have to choose the precisions in a suitable way. And amplitude estimation has a cost which is 1 over epsilon. And because we choose epsilon to be epsilon divided by log square n, the cost is also order of log square n. And this completes the estimation of lightweight elements. So I'll probably stop with this slide, which is an overview of what we do for the heavyweight elements. So recall that for the heavyweight elements, we want to actually estimate their entropy. It's not enough to simply obtain the total weight of the heavy elements. We need to actually estimate their entropy. And we do this coherently. We do the actual estimation task in superposition. So in contrast to the classical algorithm, where what you're doing is drawing samples, using those samples to estimate PI. So we know that if we draw n samples by a simple Chernoff bound, we can obtain an empirical estimate of each of the probabilities PI. That's what the classical algorithm does. The quantum algorithm completely avoids the step of estimating the probabilities. Instead, we have a subroutine which can estimate the entropy directly in superposition. And the way we do it is by using a polynomial approximation of the entropy itself. So this could be of independent interest, and so I'll just quickly say what we do. If you consider functions of the form x to the power plus or minus a for some value of a and 0, 1, and then consider the function which combines x to the power a minus x to the power minus a, it turns out that this function gives you a multiplicative estimate of log x. So these are somewhat straightforward calculations. So all you need to do is write the Taylor series for x to the power plus or minus, not the Taylor series, but a series approximation for x to the power plus or minus a. And then if you combine them to form f, it turns out that f of x is actually bounded about by log x times some factor. And in the guarantee for multiplicative approximation, what we want is this factor should be equal to gamma. And if you solve for that condition, if you solve for e to the power a log x equals gamma, then you get that a should be smaller than log gamma over log 1 over beta. So I've used the fact that x lies in beta 1 here. And it turns out that this is exactly a multiplicative approximation for the logarithm function. So we combine this approximation with quantum singular value transformations in our algorithm for estimating the heavy entropy. So yeah, the technical details are somewhat complicated, so I won't go into them. But our paper will be out on the archive soon. In fact, probably next week, and you're all welcome to have a look at it and ask me any questions if you find them. So I think with this, I'd like to end my talk, and I have a few more slides discussing the exact derivation of the complexity and the lower bound. But I'll come to the summary now. So to recall, the main idea is that we want to obtain a quadratic improvement in the sample complexity of estimating Shannon entropy. And we want to see if we can do the same for von Neumann entropy. Can we estimate von Neumann entropy with sublinear query complexity in the dimension of the state? And we answer both of these questions affirmatively. So there's a lot of scope for this line of work. And as I showed earlier in the motivation section, property testing and distributional property testing is a field which usually requires multiplicative estimates of various kinds of quantities. And these quantities could be entropy, or they could be total variation distance, or they could be collision probability. So our techniques could be applicable to many problems from this field, and it's interesting to see if we can obtain quantum speedups for classical property testing problems. And then it's an immediate question to tighten our lower bound, which I showed on the tables earlier. So we have an upper bound, which is 10 to the power 1 over 2 gamma squared, whereas we have a lower bound, which is 10 to the power 1 over 3 gamma squared. So there's a gap there, which we think can be tightened, maybe using the so-called polynomial method, for those of you who are familiar with it. And our techniques can also be extended to multiplicative estimation of other quantities, such as Renyi entropy or divergences. And this is also interesting to see, because these are quantities which are important in fact, even in machine learning, we find a lot of applications, and there is a lot of classical work on estimating these quantities. And we'd like to see if quantum algorithms for the same tasks can have any advantages in terms of sample complexity or other parameters. And of course, all of these estimation tasks, as I mentioned, can be actually practically useful. They can be used as subroutines in other algorithms, ranging from machine learning to cryptography. Okay, so that's basically what I wanted to say today. And these are some references which I can show in more detail if you're interested. And so thanks for listening.
Okay. Thanks, Sathya, for a very nice talk. Is there any question or comment? Or maybe I have one. In your estimator, you have the light element and heavy element, and you use the upper bound for the heavy element, but you choose the lower bound for the light element to put into the estimator. Why is the reason?
Okay, so I'll just come to the slide, and yeah. So sorry, could you repeat the question?
I mean, for the estimator and the light term, for the light element, why you choose it come from the lower bound?
Oh, I see. Right. Sorry. So actually, it's not just the lower bound. What we have is both a lower and an upper bound. So I didn't discuss this fully. So the left-hand side of this inequality gives the lower bound, right?
Yes.
For the lightweight. The right-hand side of this inequality actually gives an upper bound for the lightweight elements. So if you divide the inequality, if you divide the two terms on the right-hand side by gamma squared, then you see that if P divided by gamma is less than WPS times log n divided by gamma.
Yes.
So that gives the upper bound.
Okay.
Sorry, yeah. So basically, you can get both the upper and lower bounds from this inequality.
Then what about the gamma over E?
Yes, so that's a good question. So gamma over E actually contributes like an additive error. And if you recall from the complexities that I've given, there's a tilde in the notation. And if we go back to the classical complexity, there's an additive factor, there's an additive exponent of little o of 1. So the gamma over E actually causes this extra factor. It causes a small, so it's a small additive error in the estimate. And this small additive error can be made arbitrarily small by doing some technical manipulations. However, what it does is that it's kind of contaminating our estimate. And to get rid of the contamination, we need to make some effort, but the effort is sub-polynomial. Like it requires only constant number of queries, and it represents this this slowly decaying term.
When you say sublinear and it's when it's
even sub polynomial, yeah.
Well, will you go to constant when the overall symptomatic behavior go and
exactly. Okay. Yeah, so it basically it causes this additional overhead, but the overhead is not serious. The overhead is very minor.
I see.
Yeah.
How about the heavy part? You also put some in the estimator?
Yes, so for the heavy part, if you recall in the
Maybe
estimator, we just add an estimate of the heavy part. So if I come to the algorithm for the heavy part, what it does is it outputs an estimate which satisfies this condition. So can you see what I'm circling? Corresponding.
Yeah, yes.
Yeah, so the algorithm for the heavy part outputs an estimator that is almost a multiplicative estimate. So you can see that if the epsilon was not present here, this would be a multiplicative estimate. But again, there's like a small contamination which comes from the amplitude estimation step. And as I mentioned for the light case, this epsilon causes a little bit of problem, which is represented by the little o of one term.
Represented by what? Log n?
By the n to the power little o of one term.
Okay.
Yeah, so this is also absorbed into the gamma over E. This epsilon can also be absorbed into the gamma over E, and together they are represented by the little o of one term.
Okay.
Okay,
thank you. Any other question? Oh, okay. If now that's all for today. Okay, thank you for the very nice talk again. Okay, Satya, thank you.
Okay, yeah. So thanks to all of you also for listening, and Ming-Chen, thanks again for inviting me to speak about this work here. So
okay, thank you.
Okay, thanks everyone.
Okay.
Okay,
also, thanks for getting up so early.
Oh, no worries. Thank you for moving the talk by 1 hour to make it convenient for me. So it's not too early. It's like 8:30 in the morning, but I just needed a little bit of time to get ready and set everything up.
Okay, thank you, and then see you next time.
Yeah, thank you. Have a nice day.
Okay, have a nice day. Thank you. Bye.